Okay, we will see the some examples on the PMOS as well. Okay. Okay. I can do my own examples. Something like this. Point 0.8, 2 volts, 1 volt. See, in general, what will happen? Nobody will give you that this kind of approach. Actually, the arrow mark side is normally people will write with the source, okay, and those arrow mark is not there, then we write the drain. That's what the conventional approach people will do. But generally, it's not all the time correct, right? Unless otherwise, if the people are not saying anything, just you can go blindly like that. But definitely, if they're not giving anything, then you have to think about which one is the source and which one is the drain. Okay, without that kind of assumption, we cannot say that we cannot compare them. Okay, first you have to fix which terminal is the source and drain, because source and drain are the symmetrical quantities actually, because n plus n plus, there is no difference at all. Okay, so when the difference will come into the picture by applying the potential difference. Okay, then you have to decide which one is the source, which one is the drain. Okay, so that's what the importance about the MOSFETs. Okay, now what about here? So here VTP actually, whatever the VTP, VTP is minus 0.5. Okay. Now let us calculate this one. So according to this arrow mark, what we can say? It is a PMOS transistor, right? Okay. What is VCS here and VTP here? So what is the VCS here? What is the VG? VG is 1. Okay, sorry. First of all, we have to decide which one is the drain source. Which one is the drain? What one is source? 0.8 is drain. 2 volts is source. Okay. Source must be at a high potential. Drain must be at low potential for PMOS. Very good. Source, this is the drain, and this is the gate. Okay, good. Now, what about VGS now? 1 minus of 2 volts. This is a minus 0.5. Okay, this is minus 1. This is minus 0.5. What we can say? So minus 1 is actually less than minus 0.5. That's the reason why it is on. Transistor is on. Transistor is set to be on. Okay. Now, if it is on, means definitely we should say VDS. We have to compare them. Second course, VDS, VGS minus of VTP. Okay. What is the VDS here? VD is at 0.8. Okay, this is at 0.8. Minus of, what is the source? Source is at 2 volts. What is the VG? VGS minus 1. Minus of minus 0.5. Minus of minus 0.5. Okay, what it should be? Minus 0.2. Okay, what about here? Minus 0.5. 1.2 where? Yeah, right, good. Minus 1.2. Okay. Which one is less? Which one is greater or which one is less? So this is what actually. What is the region of operation? This is saturation. Very good. It is in saturation. Less than is saturation. So if you want to look at this one in the positive direction. Okay, let us do this one in the positive direction. What will happen? Okay, what we can think about it? VSG and magnitude of VTP you have to consider. Okay, what is the VSG here? 2 volts minus of 1 volt. This is a 0.5. So what is happening here? 1 volt. This is 0.5. It should be greater than, right? Then this is on. Okay, this is satisfied. Okay. Now what about this VGS, VDS? Yeah. VSD, VSG, minus of magnitude of VTP. What will happen then? What is the value? 1.2 VSG. What is the value? Okay, 1.2, 0.5. This is greater than the saturation rate is in saturation. So it's up to you which method that you'll go, which method you feel comfortable. Okay. We'll take one more example. One word I have given in this way. Usually, we always give in the positive values only, something like this. That's the reason why it's good to go with the VSDs and something like that. All these things. Okay, which one is the drain here? Source here. Which one is the source? 2 volts is the source. Okay, this is the drain. This is the gate. Okay. Now, quickly let me know what is the VSG and magnitude of VTP relationship. Please let me know. And what is the VSD and VSG minus of magnitude of VTP? Please let me know quickly. Is it greater than, less than? Which one? It is less than. Yes. 2 minus 1, 1. Okay, 1. Okay, this is 0.5. Okay, it's greater than. The transistor is on. Be greater than or less than symbol I have to use. Less than. Okay, if it is less than means it is settling. Okay, everyone, please let me know. Is it everyone is satisfied? Okay, it is in linear. But this okay. Let's check in the negative direction also, so that we'll have some good idea about that. Can you please let me know what is the region of operation of this? Which one is the gate? Of course, this is the gate. Which one is the drain? Which one is the source? Yes, this is the source. This is the drain. Okay, let me know what is this. What is the VSC and VTP magnitude? Tell me these two cases whether it is correct or not. What is the first kind? What is the first relation between VSC and the magnitude of VTP? So less than or right? Okay. So what we can say, this is cut off region. What about here now? In this case, I have to look at in this way. VGS. So greater than. What is the gate potential here? 1 volt. Minus of minus. Minus of minus. What you're talking about? Gate is at 1. Minus of minus 0.1. This is minus 0.1, right? This the source is at resistance. VG at 1 minus of minus 0.5. What is the VTP? Minus 0.5. Okay. What we can observe here? 1 plus 1.1. That is 1.1, right? Therefore, this is 1.1. This is 0.5. Which one is this one? What is the difference here? There's a conflict, right? What is the problem here? You can see gate is drain is at source is at minus 0.5. Gate is at 1. This is 0.5. Okay, this is 1.5. This is 0.5. This is what is this value? This is less than 1. If it is less than 1 means this is off, right? Cut off. It is cut off for that. Yeah. Why this problem have come? No, that's not the question. The question is that if we are changing everything is the positive direction, right? Here it is off, but here it is. What is this value? Yeah, it's correct only, no? This is correct only. So if it is greater than means this is off. Right, good. Yeah. Yeah. For the PMOS, it is greater than, right? True. Okay, so this is how we can do. Take one example. Find the ID for the given MOSFET. For the given MOSFET, find ID for the given MOSFET. And MOSFET. Whose VTH? Whose VTN is 0.5 and mu n Cox is 200 microamps per volt square. Microamps per volt square. This is the way they have given. Okay. 0.8, 1 volt, this is 0 volt. What is its ID? Drain ID means the drain to source current. Can you define? Okay. Yeah. Go ahead and do this. VTN have given, mu and Cox have given, and the potentials at each and every place they have given. Okay. You need to find out what is the ID. What is the how we are going? What is the first condition that you're doing? Fixing the source and drain. Okay. Based on that one, you have to say all the things. WL I have not given, huh? Yeah. WL by L is actually 10 micron by 10 micron. 10 micron by 0.2 micron. 10 microns by 0.2 microns. Which region of operation? It is in saturation, right? Very good. What is the current equation of it? Don't you have calculator? What is the value? Okay, some value. Hmm? Approximately something. No? I'm very poor in mathematics. 450 micron, huh? Is that true? Okay, 450 microamps. Okay. Okay, assume that somebody has, our friend has, Narendra has mentioned something like this. We go accordingly. Okay. So now the question comes here is that, okay, this is simple mathematics. Just you can substitute the values and you will get it. It's not a big deal. Okay. Now, for example, I want to change. Look at this one. The drain potential. Okay. From 1 volt to, for example, 1.5 volts. What is the ID value? If I change the drain potential from 1 volt to 1.5 volts, then what is the drain potential? Sorry, what is the ID current? I increase the drain potential from 1 volt to 1.5. What will happen? It's the same, right? Why it is so? It is in the saturation region. Excellent. Okay, very good. So as we have seen the MOSFET characteristics, as we keep on increasing this value, sorry, what is this one? The drain to source versus of ID that we know very well, right? Okay. So what is value? So this is how the characteristics is look like, right? So therefore, this is the reason from this region onwards, saturation, right? This region on saturation. Okay. Now, for example, you are at this point now. For example, you are at this point, for example. Okay. Now you increase this value VDS by some value, right? To suppose here, for example, here. Now this value is changed from here to here, for example. Then definitely you are in the saturation region. Charge on the saturation region, long channel MOSFET. Okay, the current is constant. It is not at all changing. Okay, that's the reason. That's what you have to remember. Okay, if I ask you that at what value of the VGS, sorry, what value of the VDS will enter into the linear region? What value of the drain potential? What value of drain potential? Sorry, what value of the gate potential? Okay, instead of the drain potential, we talk about the gate potential. What value of the gate potential will make this MOSFET enter into the linear region? How much that should be? What is the condition for it has to go into the linear region? Okay, as we know very well that if the drain potential is equal to Vc minus of Vtn, then this is the place where exactly the edge of the saturation. That means this is the point. This is the point we are talking about. What is this point is all about? The VCS minus of Vtn. So therefore, when the VDS value is exactly equal to VCS minus of Vtn, then it is in the edge of the saturation. It can go either the saturation side or it can go either linear side. Okay. Therefore, but when you this is what the very important point, right? But our question is that we want to enter into the linear region. Therefore, what gate potential than that of the drain potential? As we know that people are saying that the gate potential is more than that of more positive than that of drain potential. But what is the value that I'm asking? One thing is good that you know that the drain per gate potential should be more than that of the drain potential. Okay, but what is that value? How do we calculate? This is simple, right? From here we can say, so VDS here. Okay, here we sorry the source we can remove. Why? Because for this same potential for the this side and left side and right side, right? VD, VG minus of VT. Okay, therefore this is called VD plus VTN. Here we can write VC. Okay, if this value is less than, that means VC value is more than that of whatever the drain potential is there, that is above just one threshold above it is sufficient. So what value that I have to apply now here? What is the drain potential actually here? 1 volt I have mentioned, right? What is the potential? 1 volt. Already in the given example, I have given 1 volt, right? Yeah, drain 1 volt. Just you add one potential. One threshold, 0.5 threshold. Should be the gate potential. Should be the gate potential. So therefore, what is the value? Therefore, minimum 1.5. Okay. So that means should be greater than, I can say. That means VC value minimum 1.5 if you maintain, then definitely you will enter into the linear region. If it is more than 1.5 is absolutely fine. Definitely will go into the it will deeper into the linear region. If the VC value is more than 1.5, deeper and deeper, 1.5, 1.7, 1.82, 3 volts. If you go and higher values, it will go deeper into the linear region. Not cut off because it is more than VGS is more than that of threshold voltage, right? It cannot go to cut off already because VGS is more than threshold voltage. Am I right or not? Okay. So that's how we have to identify. Okay. If you want to make this is a more triode region, more deeper into the saturation, what do you have to do? More deeper into the saturation. So more deeper into the saturation means this side. Okay. Okay. Therefore, this is what more deeper into the saturation. More deeper into the linear means this one. What do you have to do? What is the drain potential then? Drain potential is much more than that of gate potential. Okay, that's how we have to think about it. because this is very important when we are realizing the circuits. We want to operate the transistors more in the saturation region. Okay, because for the amplification purpose, we are creating these analog circuits. Okay, and be careful that you should not enter into the linear region. Then we have to know that what drain potential that I have to apply in order to avoid to go into the linear region, or what VC we have to apply so that it should not enter into the linear region. Are you getting the point? So these points are very essential when we talk about the analog IC design. Hopefully you catch this point, right? We stop here today, and tomorrow we will see the remaining things.